Hello students, very warm welcome again. I'm Abhishek Kumar Chowdary, your physics lecturer, and I'm working at Sri Chaitanya Goshala campus. So we are now almost at the end of our discussion of nuclear physics. But see what interesting journey it was. We started from what is proton and where we reached in the previous session. It was the proton-proton cycle. And proton-proton cycle, then if you remember, the pair production, pair annihilation, and the source of, that energy, helium and hydrogen, that in sun's core, everyone, the temperature 10 raised to power 7 one there. This was the proper discussion of the previous discussion. Okay. So now, today, we are going to discuss one more very interesting topic. And that topic is carbon-nitrogen cycle. Proton-proton cycle was the topic of previous class discussion, and today it is carbon-nitrogen cycle. Tell me one thing, have you ever heard about the solar energy? Solar energy. It is quite in the present era, and this is being used as an alternative form of energy. There is a railway station, I think it's Guwahati, which completely works on solar energy. It's a very strong source of energy. Do you know from where the concept of this solar energy actually came? Bothe and Becker, these were the two great scientists. They thought that solar energy is basically due to carbon-nitrogen cycle. Just concentrate on the word what I'm saying. I'm not saying carbon-nitrogen fission or carbon-nitrogen fusion or carbon-nitrogen nuclear reaction. What I'm saying is carbon-nitrogen cycle. So this is a proper cycle, a 6-step cycle. What happens here? What is the energies liberating there? What are the ingredients there? That says the topic of today's discussion. Okay, let's start. Carbon-nitrogen cycle. Mainly responsible for solar energy, right? I just told you that. Hydrogen is converted into helium. Now, this is the input, this is the output. What is being converted? Hydrogen into what? Helium. Hydrogen to helium. But by the help of carbon and nitrogen as catalyst. Carbon and nitrogen as catalyst. This is the 6th step process. After the 6th step, again carbon, nitrogen, they act like a catalyst. Again reaction starts. This is a cycle of 6 steps. Okay. So this is basically the source of solar energy, and a very significant amount of energy is liberated there. So let's see the entire mechanism. What exactly is carbon-nitrogen cycle? But before moving to the mechanism, 2 question points in mind. First, responsible for solar energy is which cycle? Carbon-nitrogen cycle. Next, hydrogen-helium conversion takes place in which cycle? This is again in carbon-nitrogen cycle. And in carbon-nitrogen cycle, carbon and nitrogens are catalyst. Fine. Now come to the mechanism. See here. This is C12-6. Okay. This is being, you can see here reactant. This is 1H1, proton. Now again a question point. This is what you know. What is this? This is a nuclear projectile. I told you the alpha particle, the neutron, the proton, all these act like nuclear projectile. So in carbon-nitrogen cycle, who is acting as a nuclear projectile? The answer is proton. So this proton here is nuclear projectile. In carbon-nitrogen cycle, proton is the nuclear projectile. Okay. So C12-6 bombarded with projectile is proton, and this is being converted into nitrogen-13. Product is nitrogen-13. You know what is nitrogen-13? It is radioactive. Nitrogen-13. This is radioactive. Radioactive. Obviously energy will be released there. So gamma is indicating the photon energy. So from where we started with the bombardment of C12 with the nuclear projectile proton being converted into nitrogen, nitrogen 13, and my students, nitrogen 13, do remember, is radioactive. And obviously energy is being released there. Radioactive, when I'm saying nitrogen 13 is radioactive, what actually I mean to say? Unstable, transient product. It not will be a stable product. Okay, nitrogen 13 is formed, reaction is over. It's not the case. So what happens next? Now the second step. This was the first. I told you 1, 2, 3, 4, 5, 6 step cycle. Now comes to the second step. Now this nitrogen 13 radioactive, it is whenever in carbon nitrogen cycle, most often you will see if something is unstable, it is getting stability by releasing a positron. Positron, if you remember, positive beta decay. So here N13 radioactive is releasing a positron, E0 plus 0, because we assume that mass is so less, there is negligible mass, but 1 plus 1 is the charge, so this is the positron. Now it is releasing positron, and from 7 it is converting into 6. So C13, there is one of the isotope of carbon is formed in the second step. First step, radioactive nitrogen. Second step, isotope of carbon, C13, by releasing what? By releasing a positron. So positron is released. I told you, I'm repeating this, whenever there is something unstable, most often you will see they are trying to get a stability by releasing a positron. So this is the positron. And again, I'm recalling you the positive beta decay. If there is a positron, there was a neutrino. So neutrino is there. So this is the second step. Now come to the third step. Now we have isotope of carbon, carbon 13. Again this carbon 13, first carbon 12, now carbon 13. Again this is a nuclear projectile. This is bombarding it, again C13 proton, and now the natural nitrogen, nitrogen 14 is formed, stable one. Stability means energy will released again, and that energy is again in photon region, so this is called gamma. Nice. Now what is the fourth step? Natural nitrogen is again carbon nitrogen cycle. Nitrogen is again being bombarded by what? It is being bombarded by again the nuclear projectile. It's quite interesting to say that in a proton cycle, in fission, in here the carbon nitrogen cycle, we are changing the projectiles, and this is also a question type. A very small question type. If not from, suppose they're not asking you it from nucleus, they might asking you for the fundamental of physics, physical world they might ask you. So in carbon nitrogen cycle, the projectile is proton. Please note it down, make it an important point. This natural nitrogen is being bombarded by proton again. What is being formed? Oxygen 15. Energy is released. Fifth step. This is again to nitrogen. First is for natural, then it's isotope, nitrogen 15, and again unstable. What that unstable is releasing? Positron to get stability. Positron, then neutron is also there, positive beta decay, and energy is releasing. Okay. After this fifth step, oxygen 15, see here. What is happening? You have formed this nitrogen 15. Nitrogen 15 almost in every step, either positron is releasing or hydrogen is being bombarded as a projectile. This nitrogen 15 is again bombarded by what? It is being bombarded by a proton. Now what is being formed? Being formed is C12 and the product helium. Now did you notice a very interesting thing here? Let me show you this. From where we started, C12, and where we reached, C12. Did you notice the cycle? So the carbon-nitrogen cycle, a 6-step cycle, and after that 6th step, again the carbon, again the nitrogen, there will be catalyst to start the reaction again. So this keeps on going, this is a 6-step cycle and it keeps on going. We started from carbon and we reached at carbon in the 6th step. But our product that was desired was helium. So from where we started from 1 hydrogen. Let's see, interesting thing. 1 hydrogen, fine. Let's search for hydrogen. 2 hydrogen, okay. 3 hydrogen, okay. 4th hydrogen. And let's see this. Hydrogen is converted into helium. So how many hydrogens are there? 4. Final reaction. The summary of the 6 reactions, 6 steps. 4 hydrogen are being finally converted into what? Hydrogen to helium. 4 hydrogens are being converted into helium with positron and neutron, and obviously gamma energy is released. So energy is released, that's the obvious process there. But this is the result of carbon-nitrogen cycle. One thing is there, in the final box, if you will see, there is no carbon, and students, there is no nitrogen. It means carbon and nitrogen as the catalyst, they are not there in the final product, are they? They are not. So hydrogen, helium, but carbon, nitrogen are being used as catalyst, and hydrogen for carbon and nitrogen catalyst used as nuclear projectile. Okay, now let's see the energy released. Let me tell you, this energy released that you are looking here, the data, this energy released is energy of both gamma and neutrino. Both, energy of both is there. Basically, what is this energy? Energy is mass of reactant, mass equivalent of energy, mass of reactant minus mass of product. How this is being achieved? This is very simple. Mass of reactant minus mass of product into C square. This is this energy. And this energy of what? Whose energy is this? This energy is of gamma and this energy is of neutrino. Okay, there. One more interesting fact is, see, carbon-nitrogen cycle begins in stars at 2 into 10 raised to power 7 Kelvin. If you remember, I told you the data for proton-proton cycle in sun for 10 raised to power 7 Kelvin. At that temperature, there is no carbon-nitrogen cycle, students. It starts in almost double the temperature, 2 into 10 raised to power 7 Kelvin. So these are the small facts, and we have done with the mechanism as well. So do remember, the main source of solar energy, carbon-nitrogen cycle, hydrogen is being converted into helium, and carbon nitrogen are acting as a catalyst, so you will not see carbon nitrogen in the final product. Hydrogen for carbon and nitrogen is acting like a nuclear projectile, and this is a cycle which is being repeated after each 6th step. So this was the carbon nitrogen cycle for you. Now coming to some more interesting applications of radioactivity: fission, fusion, proton cycle, proton-proton, carbon-nitrogen cycle. Have you ever thought that we should have the enormous amount of energy? We quite often go through the problem of power cut, or we know that there is no much of the electricity you cannot use for the infinite time. It is electrical energy is what? Some other energy is being converted into electrical energy. Energy conversion is taking place. And we have here discussed that in fission, or in cycle you can see, in cycles, the energy is reproduced. So why not electrical energy? So if we will take the input as, nuclear, here you can see, if we can take input as thermonuclear fusion, then there will not be any deficiency of any shortage of the power we are using. How to achieve this? I mean to say, is this possible? Can we achieve this? We can achieve this. Most of the countries, including our country, we are working towards it. Working towards what? Working towards controlled thermonuclear fusion. So this controlled thermonuclear fusion is, see what is this? Controlled thermonuclear fusion, you know, controlled, you know, that number of projectiles can be controlled and used to generate steady power by heating the nuclear fuel to a temperature. Now here comes the actual thing. You have to actually heat the nuclear fuel in a temperature range of 10 raised to power 8 Kelvin. Do you know what is the biggest challenge in this? The challenge is where that nuclear fuel should be kept. What utensils, what substance, what element is going to bear that temperature? So we are actually working towards this only. The biggest challenge is this only. If 10 raised to power 8 Kelvin at this temperature, there can be, you can find, or I can find, or we can find some, materials in which the nuclear fuel can be kept. Then okay, that's done. The mega hurdle is gone. So this is basically this temperature maintenance for the nuclear fuel is, and to take the container to contain the nuclear fuel. These are the real challenges in this thermonuclear fusion. See, now a technical thing here. At 10 raised to power 8 Kelvin, fuel is mixture of, your question point is this. At 10 raised to power 8 Kelvin for controlled thermonuclear fusion, what exactly is the fuel? Fuel is mixture of positive ions and electrons. And my dear students, these electrons are what? Plasma. These electrons are plasma. So at this temperature, fuel is mixture of positive ions and electrons are plasma here. Okay. Now some more interesting question point for you people is, first point, important point. In the sun, both proton-proton cycle and carbon-nitrogen cycles occur with equal probabilities. Equal probabilities. See, the temperature for beginning of these two cycles are different. For proton-proton it is 10 raised to power 7. For carbon-nitrogen it is 2 into 10 raised to power 7. But here the probabilities to occur is equal, is same. And the second point, in dwarf star. Okay, what is this? What is the dwarf star? Temperature at the core of the dwarf star is less than the temperature of sun. So we are talking about the stars whose core temperature is less than the temperature of the sun. In such cases, proton-proton cycle, this dominates the energy generation. See, in sun though we have discussed there is equal probabilities of carbon, nitrogen and proton-proton. They both can generate energy with equal probabilities. But in case of a temperature which is less than the temperature of the sun, that is a dwarf star, there who is dominating? Proton-proton cycle dominates the energy generation. And obviously if temperature, sun's temperature is the reference, if temperature is less than that, proton-proton will dominate, temperature is greater than that, carbon-nitrogen cycle dominates. So these were some important concepts, some question points, and we wish that if controlled thermonuclear fusion is quite achievable, there will not be any shortage of electrical power. So my dear students, my future doctors, till now we have done carbon-nitrogen cycle, and we also discussed a very small, briefly we discussed that controlled thermonuclear fusion. Okay. Here is some more information about radioactivity and more useful in your medicine studies is radioisotopes. You know the radiology and these things. So radio is from radioactivity, radioisotopes. Radioisotopes, very first you have to know the definition. What is the definition? Definition is radioisotopes having very small half-lives. This is the unique characteristic of radioisotope. Before even discussing this topic, we have done one radioisotope where in carbon nitrogen cycle, nitrogen 13. I told you that nitrogen 13 was radioactive. Isotope of what? Nitrogen. So it was radioisotope. So what radioisotope actually does? Radioisotope is so useful. Being used in almost every aspect, like you can use it in agriculture, you can use this in chemistry study, you can use it in industry, and in your, my future doctors, in your future practice of your medicine, this radioisotope is going to be very important. Okay, so let's see some of the radioisotopes. See this reaction. Aluminium being bombarded with the neutron, obviously the nuclear projectile, converting into sodium. Now see this. What do you think? What is this? Isotope of sodium. And this is a radioisotope. Radioactive radioisotope. It is having a very small half-life. You know where this sodium isotope, radioisotope of sodium is being used? This is used in the study of circulation of, blood in the blood vessels and all. In such type of diseases, the proper circulation of, even suppose to some patient medicine has been given, so that medicine is properly circulating or not in the blood vessels, that is being detected by this sodium isotope. So this is just so important for my future doctors. Next, phosphorus 31. With this deuterium, what is being formed? Phosphorus 32. And what is this? This is again a radioisotope. So this is radioisotope. Generally phosphorus radioisotope, if I would suggest you for supplementary information, this is used in your skin disease treatment. Skin disease treatment. So isn't it a physics much related to your biology? At times I have seen students saying, why physics is there in medical and NEET, why physics is there? And at times you must have heard or thought that also. But this is so much important. Nuclear physics, radioactivity you are dealing. My future doctors, this is going to be in your studies also. So this phosphorus, this is used for skin disease. And the most important one, see here, cobalt 59, neutron, cobalt 60. What is this? Radioisotope of cobalt, and this is used in cancer treatment. This is used in cancer treatment. And energy is released obviously. So these were the three examples I gave you to understand that radioisotopes used in the field of medicine. There's some more use, and this is the use that we used to listen from early classes. Have you ever heard of the method called carbon dating? C dating. Why C dating is used? It is used to determine the age of fossils. Age of fossils is being used by this. And in this C dating, what we are using is C14. What is this? C14 is again, it's a radioisotope. Radioisotope of what? Carbon. Radioisotope of carbon. So see the various uses of radioisotopes almost everywhere. I told you, in agriculture, in industries, in medicine, it's almost everywhere. Also, one of the uses, this is important, this is your question point also. Keep on asking this. used to detect flaws in metal structure. There are some, I'm not talking about this. There's some radioisotopes that we use to detect flaws in metal structure, and such radioisotopes are used in the industries. So radioisotope, if you are if you will somewhere study, okay, this is radioisotope, will be in your mind, they are the isotopes with very small what? Half-life. And they are of much use, much significance, so useful. Now we are concluding the fusion-fission concept, and a very quick revision, the difference between these two. Fission, fusion. Heavy nucleus splits, we know, heavy nucleus from the right-hand side of the binding energy curve. And lighter nuclei combine, but do remember these two are the exoagic. Both are trying to go towards the stable nuclei. Okay. Neutrons are required as a projectile. Protons are required in fusion. Okay, nice. Next one. Possible at normal temperature and pressure. Okay. But we have discussed in fusion, high pressure and high temperature are required. You cannot have that combination of lighter nuclei at normal temperature and pressure. Energy, if you remember, we have discussed in fission, energy released is greater, but energy per nucleon is lesser. So energy per nucleon is 0.85 and energy per nucleon is 6 mega electron volt. It was, if you remember, we discussed almost 7 times greater. Mass defect for this energy per nucleon is 0.1%. The reactant and product mass difference is almost 0.1%. And mass defect in fusion is 0.7%. There are many more, like if fissionable materials are not that cheap, like uranium, quite costly and quite rare also. Moreover, for fusion, the fusionable materials are cheap. Secondly, in fission, the radiations are very harmful. In fusion, the radiations are not that harmful. So these are the basic quick revision and the difference, and also important from examination point of view, the difference between fission and fusion, a quick summary. Many interesting concepts we have done, we have discussed, but these concepts are half done unless we are going to discuss numericals, the question varieties on them. So in our next lecture, we are going to see the numerical varieties on the fusion, the fission, the cycles, what type of questions, varieties are there, numericals. But before that numerical, what you have to do, you have to revise the entire fission and fusion for that. The energy concept, the reactions, you have to go through them, see them, then we will discuss numericals, then that topic for you will be a completely strong topic, and it has to be strong because you have to get 180 out of 180 in physics, and you have to get 720 out of 720 in NEET. Let me tell you, every year 180 marks are generally achieved by students. In physics, 180 marks are generally achieved. I personally know some students. So this is not a very difficult task. What you have to do to be prepared for each and every line of that chapter. Each and every line of that chapter. See, if you can achieve 160, you can say 170, you can easily achieve 180 also. So these lectures are in-depth lectures are there, each and every details are there to help you to achieve your 180 marks. So what is our target, students? To achieve 180 out of 180 in physics. Sri Chaitanya will help you in this. I am just now concluding this. Very all the best, and don't miss the next lecture that is going to be on numerical varieties. Till then, happy learning. God bless you. Bye-bye.